Thank you.
Hi, I'm Anjitha. I'm in final year PhD student in computational cosmology group, Poland. So today I will present our work on photometric redshifts and angular clustering of quasars within the kilodegree survey. This project is supervised by Maciej Biliski and Wojtek Helbing, and in collaboration with the Shimon and Priyanka. They are my postdocs. The talk is mainly divided into three parts. First, I will explain how we estimated photometric redshifts of quasars. Then, I will describe the angular clustering and quasar bias estimation in photocy bits. So, some galaxies are called active galaxies because they have a supermassive black hole at their center. Matter accretion onto this supermassive black hole quasar central region more luminous compared to the rest of the galaxy. This central region is called active galaxies or active galactic nuclei. Quasars are the most brightest AGNs in the universe. Because of their high luminosity, they can be observed up to very high redshifts. So this makes them very valuable tracer to study our universe across cosmic time. Marika introduced the kilodegree survey, so I'm not going into explain what is KITS. I'm also a part of kilodegree survey collaboration. We are using KITS DR4 quasars. Actually, this selection of quasars done by Shimon in his 2021 work. This selection was photometric. This method is purely relies on magnitude and colors. He selected this quasars within KITS DR4. We are using this KITS DR4 for photocy catalog, photometric catalog. So to estimate a photometric redshifts, we used a hybrid C. Actually, this method, this is a deep learning package originally developed for KITS DR4 bright galaxy sample. For more details about the model architecture and everything, feel free to check my paper. Hybrid C uses both 9-band magnitudes and 4-band images. Then the data is trained on spectroscopic redshifts. This is obtained from the recent database DESI DR1 and SPSS DR17. So hybrid C is trained and tested on data. In this slide, I'm showing the test results. So to assess the model performance, we used standard metrics. Mainly the bias, it's the average offset between photocy and spexy. Then the normalized bias, it's a scaling of bias. Then to account the scatter, we used standard deviation and SMAN values. The overall statistics shows better performance of our model compared to the state-of-the-art quasar photocy techniques. So now we have a model for photocies. Then we derive the photocies for KITS DR for quasar objects for all objects. This was around 157,000 objects. This photocy catalog is divided into 4 bins, 4 tomographic bins. From redshift to 0.1 to 2.7. This redshift range is chosen because most of the quasars are occupied in this region. So we are dealing with the photometric cataloger. So our observable is the angular 2-point correlation function. 2-point correlation function quantifies the excess probability of finding a pair of quasars separated by an angular scale theta. So angular 2p is measured in angular ranges from 0.05 to 1 degree, and we used a Lendület estimator for covariance estimation and this angular clustering observational measurement. We used a trade core package. But this quasar cataloger, that means the classified quasar cataloger contaminated by stars. So this motivates us to use stellar contamination correction in the angular clustering measurement. So we used a stellar contamination correction formula from Mayer's et al. 2007 paper. So we constructed a star cataloger in KITS DR4 and measured the omega s, that is the autocorrelation function of stars. Then we used this formula to correct the observed quasar autocorrelation function. Here, A is the purity parameter of this DR4 QSO classification model. In our case, it is 0.98. Now we have an observational measurement. Now I am moving to the theoretical prediction. For the theoretical prediction, first we predict the angular clustering of total matter in our universe. For this, PM is the nonlinear power spectrum. Nonlinear power spectrum. For all these theoretical prediction, we used the core cosmology library. In that library, to predict the linear power spectrum, it uses class algorithm. Then the halo fit-based nonlinear correction is applied. Then we take the legendary transformation to get the angular 2 PCF of matter. So you can see here the dn by dz is the input from our side. It is the redshift distribution of tracer. That means redshift distribution of quasar here. You can see in the figure, I'm showing the redshift distribution of quasars in 4 redshift bits. So this now we have angular 2 piece of matter and the angular 2p correlation function of a quasar. This is connected by a bias factor. Here we assumed a scale independent linear bias. So in each redshift bin, this bias is inferred through chi-square minimization. This is the key plot in this talk. You can see here at small scale, that means the physical co-moving transverse distance is less than 10 megaparsec. The halophyte-based linear power spectrum is not is less reliable. That's why we exclude those nonlinear regions from the fitting. We only used the linear regime. That means we estimated the linear bias, and you can see I'm showing. So can you see this figure clearly? Is it clear? Okay, I will show. Okay. This is the main result because the bias is increasing with redshift. That means the at higher redshift the quasars are leaving the most massive halos. So this is the main result we get. So the main conclusions and the future aspects of this work is we estimated photo-C estimation with a deep learning model and a better training set, because here the photo-Cs of quasars are improved because of the better training data set, the CDR1 and the STSS-DR70. And the quasar bias estimation is very sensitive to the redshift distribution. And we are preparing our paper, and in that paper we detailedly discuss how the redshift distribution affects the quasar bias estimation. The future aspects is here we used 4-band images and a 9-band photometry. We can also use 9-band images and a 9-band photometry. Then we can calibrate our redshift, that is a redshift calibration by using some self-organizing map techniques. Then here we calculated scale independent quasar bias. We can also calculate scale dependent quasar bias by using the techniques halo occupation distribution models. Then extend our analysis to the deeper KITS DR5 quasar sample. These are the future aspects of this work. Thank you. If you have any questions, and you can contact me. This is my email ID. Yes. Any question? Yes.
Nice talk. So you included spectroscopic redshifts from SDSS-DR17. Somehow there were a problem with DR16 redshifts, which they also talked about. Was this an issue in 17? Okay, and did it make harder your work?
No, I think we cross match because DESI DR1 and the SDSS DR17 spectroscopic data is cross matched with the KITS DR4. I think we didn't find any problems. Yeah, maybe we are not aware.
Thank you.
So you said that in future you want to analyze with scale-dependent bias. So are you sure now that your scale cuts are such that your galaxy bias is linear?
You mean the R greater than 10 megaparsec?
Yeah.
Okay, because the theoretical prediction is based on halo fit based on. So that halo fit based, we understood halo fit based theoretical prediction is less reliable in the 10 raised to megaparsec because the nonlinear effects are more dominant in those regions. That's why we are in the safe side, only use the linear regions. Yeah.
So when you said halo fit, you mean the Takahashi halo fit?
Yes, exactly. Yeah.
And then you have linear bias multiplied by that.
Yes, class algorithm from the linear.
Yeah.
Yeah. Yes. Yeah.
Yeah. Because halo fit doesn't have galaxy.
Yeah.
Bias.
Yes.
Yeah.
Yeah.
Because the thing is that's different. Like halo fit was for math power spectrum, right?
Yeah.
And then you have to assume something for galaxy bias, and then you have to assume where it becomes nonlinear, this sort of thing.
Yes, this is done by chi-square minimization technique.
Okay.
Yeah. Yeah, because the scaled version. Yeah, B square WM. Yeah. That is the angular 2D safe of matter. Then. Oh, okay, because this is from the left hand side is the omega m is from the theory, that is halo fit, that is a matter. Then the Q is the quasars. This is connected by the bias. Then bias is estimated by chi-square minimization.
Yeah, but like how do you set like your scale cut to make sure that you can use this formula?
In this figure, we just didn't use those points, just exclude those points.
Yeah, but why those? Why not like push it this way?
Okay. This is calculated by the we find the effective redshift and then calculate. Then we take the theta. Then we find the physical distance. Then we just cut. Okay, the points are less than 10 megaparsec.
Okay, so you decided 10 megaparsec is safe, and then
yes, yeah, at effective redshift. Okay.
Thanks, Anjitha.
Thank you.